All right, so this is the second half of the lecture, and we are going to be talking about fracture toughness and some other material properties. So fracture toughness is a material property. It's not the same as the modulus of toughness that we just talked about. It is a material property that defines a material's ability to resist a crack. Okay, so when you have a crack, you have a very sharp point, and if you have any forces at that point, the force divided by the area, which is really small, results in really high stresses. If you have a ductile material, that material will give, and that's a good thing. If you don't, you have a brittle material, that crack can propagate. And we can calculate the effect of that crack for that material using that using a stress intensity factor. We'll spend some time talking about that later. And we can compare that to the fracture toughness, and when the stress intensity factor, which is not the same as the stress concentrations. So it's really important in this class and with materials that we get our language correct. You know, stress concentration, we're talking about geometry, changes in cross-sectional geometries, which cause stress risers. It's not the same as the stress intensity factor K. That's related to the effect of a crack in material, and all materials have cracks, and so we can estimate the nominal crack size for that material to get an estimate of its stress intensity factor, and then we can compare that to the fracture toughness to see if those cracks are going to cause a problem and if failure is likely to occur. If a failure occurs in this mode, it can be catastrophic and deadly, and so that's another material property that we have to keep in the front of our mind as we do design. Now, when we have a brittle material, a ductile material that's subjected to cyclical loads, it can often fail in a brittle fashion at loads below the yield stresses or ultimate stresses. Okay, we'll spend a lot of lectures talking about fatigue, but it accounts for over 90% of the machine failures and billions of dollars annually throughout the world of costs for failed machines. Now, the data that we have is for fully reversed loads, where we have a stress that cycles between positive and negative over time with a zero mean. We also have other cases of stress that we have to deal with, where we have repeated stress, where we only have like a non-zero stress over time. And then we can have fluctuating stresses, where we have a mean stress that also fluctuates. Most of the data that we have available is from this test here, which is from the Moore test. Okay, and these tests were summarized in a Wooler diagram. Sometimes they're called SN diagrams. This is not just for steels, but other materials. And so this is the Wooler diagram here. And for some materials, what we do when we construct this Wooler diagram, we start with the ultimate tensile strength of that material, and then we look at the number of cycles that it has a fully reversed stress, okay, and the amplitude of that stress, and then we see where these materials fail. So this is the failure line for materials at different stresses. And so as you can see, we start with the ultimate tensile stress, but we get failure here along these lines if we have a repeated stress for this many number of cycles. We'll spend a lot more time talking about this. I'm just kind of trying to put all the concepts of materials that you kind of need to keep in mind as a material designer. Okay, now for some materials, such as some steels, you can get an endurance limit. Okay, so this is often a design target where even if you increase the number of cycles, as long as you stay below this stress, you can theoretically run forever. Okay, now other materials such as aluminum, magnesium, copper, nickel alloys, some stainless, and high carbon strength and alloy steels don't have this endurance limit. They don't have this knee in the diagram, and their life just continues to go down as the cycles go. So if you have sustained cyclical stress in this artifact, you will eventually get failure for those materials. Okay, some people think that's why some airplanes older airplanes will fall out of the sky that were completely maintained. It's just that the load somewhere in the aircraft got out to here and then caused catastrophic failure. Okay. So there is an endurance limit for many low-strength carbon steels, alloy steels, some stainless steels, irons, molybdenum alloys, titanium alloys, and some polymers even. Okay. But, depending on the material you choose, if you expect, repeated loads, then you have to design for very, very high cycle fatigue. This is usually below 10 to 3 is like low cycle fatigue. If you have to design for high cycle fatigue, then you need to make sure you pick a material that has an endurance limit. Okay. Now, let's talk about hardness. So the hardness of a material is a very important property for the machine designer. Because it can be an indicator of its resistance to wear. It's not a guarantee. There's tests that we can do, which are the Vickers, Burnell, and Rockwell tests. The Burnell hardness test is probably the easiest to do. They all involve the same approach, where you basically hit the material with something that's very, very hard, some stylus, and you look at the dent that the stylus leaves in the material under that load. And since you know the load that you're applying, you can look at the dent and you can get an estimate of the hardness. They don't all have the same accuracy. It's actually not very easy to go from one hardness to another. We'll show you a table how you do that. The Burnell hardness is pretty easy to obtain experimentally, and for steels, the ultimate tensile strength can be directly related to the hardness using this equation. This is in PSI. If you want to use SI units, this is the equation. Obviously, you see that they're not the same. Okay, so the units matter, but the hardness can be directly related to the strength for some materials if you have to obtain them experimentally. This is a mapping of the hardness and the ultimate tensile strength for steels. Okay, so this is your Burnell hardness, this is your Vickers, these are your Rockwell. There's two different types of Rockwell tests, and then these are your strengths for those materials based on the hardware. So if you have hardness test data, you can get an estimate of the ultimate tensile strength of that material. Now, let's talk about heat treatment. So when you design machines, you have to make a lot of decisions about the materials that you're using. And there's really a lot of options to choose from. So, once you define your geometry and you kind of get your material properties and strengths, then when you go to buy it, if you're a junior designer, you may realize that, they are saying, do you want quenched, tempered, annealed, normalized, what all these things mean. So I'm going to just cover them briefly here, just so you can kind of get a lay of the land. Steel is just an alloy of carbon and iron, and you have other steel alloys that have other elements added to them for different properties. The higher the carbon content, the greater the ability to harden a steel. So low carbon steels will have about 0.03 to 0.3% of carbon. Medium carbon steels will have about 0.35 to 0.55% carbon. And high carbon steels will have about 0.6 to about 1.5% carbon. We call cast irons have greater than 2% carbon. Okay, so low carbon steel doesn't have enough carbon to through harden it typically. Okay, where we harden the steel throughout, and it must be surface hardened. Medium and high carbon steels, they can be traditionally heat treated through heating first and quenching, optionally tempering, and optionally annealing, and optionally normalizing. So let's talk about those terms. So for medium and high carbon steels, if we want to make them harder, we can quench them, which we basically heat above their crystallization temperature. In this case, it's about 1400 degrees Fahrenheit. And then we can quench the steel by dumping it in a room temperature bath of oil. Okay, this will produce martensite, which is a brittle form of the steel. And if you can see here, these are not to scale, but you can see that we have a much stronger steel here by quenching it, but it's much more brittle. After quenching, it can be tempered. Okay, so after we get that martensite, we can quench it at a lower temperature, below the recrystallization temperature, 400, 1300. Okay, you basically heat soak it and then cool it slowly to convert some of the martensite to the other steel phases, such as ferrite, cementite. So it'll reduce the strength, but it'll increase the ductility. Okay, so this is where you're going to get here if you temper it. Okay, so you get these different properties. So if you care about the fracture toughness, the modulus of toughness for that material, okay, then these are the trade-offs that you're making when you select a material. And then annealing can reverse the process of quenching. Okay, and so even you can take the raw steel, that hasn't been quenched, and you can anneal it. But essentially, you heat it, okay, but instead of quenching it, you keep it at higher temperatures, okay, and you kind of design that temperature profile. And this is the whole point of your materials class, where you can kind of look at these eutectic diagrams and find the phases that you want. It can restore the metal to its unhardened state, or it can be applied simply to reduce the residual stress and strain in the steel. But you can change those the microstructure of the steel to have different properties that you want. Okay, so normalizing is similar to annealing, but the process is a little bit faster. Okay, so you don't fully complete everything. Okay, and that can result in a normal and harder steel. So these are kind of the different processes that we use on steels. And when you buy a material, you can buy the material, that's been tempered, annealed, or normalized, and should kind of have at least this high level view of what's going on. Now, when you have low carbon steels, there's not enough carbon to harden it all the way through. Through hardening is kind of what you had just talked about. And when we do through hardening, it can create the residual tensile stresses, which is not good for fatigue. So tensile stresses on the surface and fatigue are never really good friends, but what it can do is increase your wear resistance. So the heat treatment's relationship to fatigue, which we'll talk about later, is a big deal if we expect cyclical loads. If not, we can just stay with our required strengths and then pick the material that best suits the needs. Now, case hardening also, increases wear resistance and hardness, and it can be done with a lower carbon steel. And the way that it's done is through carburizing, where you basically have a carbon-rich gas environment at elevated temperatures. It causes these carbons to diffuse into the surface of the material. And similarly, nitriding, where you have a nitride salt or gas, they will cause the nitrides to go into the surface. And then you have cyaniding, which increases both the surface carbon and the nitrides. Okay. What that does is actually adds these materials to the surface, which increases their content of that material. So we know that higher carbon results in a higher strength steel. And we can also do for low carbon steels, we can do carbons. For medium and high carbon steels, we can do flame hardening and surface quenching or induction hardening. And basically where we're sort of doing the process of quenching, but just on the surface, where we heat the outer surface and then we cool it quickly by spraying some water or oil on it to quench it and try to change that surface to become a harder surface. These carburizing, nitriding, cyaniding, it causes a change in volume of the material because you're adding these elements, Okay, and that actually is a good thing for fatigue because it creates compressive residual stresses. So this graph here is just if this is your material, this is the surface of your material, and this is going into the material. If you look at this is a 0, so this would be no stress. This is negative. Okay, so these are compressive stresses. Okay, and so when you carburize or nitride, what happens is you actually create these compressive stresses in the material here. And you can see that a nitrided material has a lot of compressive stress that's real close to the surface versus a carburized material, which has a little bit lower compressive stresses, but they go deeper in through the material. So there's a lot of dynamics here, but the point is that you can harden a mirrored material, and often that's required for some application where you have to have good wear resistance or good fatigue resistance. If we zoom this all the way down for this carburized material from the top surface to the bottom surface, this is what it looks like. So you can see we have these compressive stresses at the surface here, and those are balanced internally by these tensile stresses, and then back up to these compressive stresses. So you can see that we have now these residual stresses in the material, but these residual compressive stresses at the surface can be make the material less susceptible to fatigue and make it harder, which can increase its wear resistance. All right. Some non-ferrous metals can be heat treated through precipitation hardening or age hardening. Example is an aluminum alloy with about 4.5% copper. So that can be done. Hardened aluminum can approach the strength of some of the medium carbon steels, and because aluminum is a third the weight, then you can have a same strength, lower weight application, but obviously your expense is going to go up because of the cost of aluminum. Another way that we can make materials harder is through strain hardening or cold working. And that's essentially where we just, manipulate the material below its recrystallization temperature. So this is used for a lot of stamping and drawing and a production of small formed parts. If you're going through this process here, you're pretty much following this here where if this is your material, you have a ductile material, this is your stress strain diagram, you exceed your yield stress and then you release that stress. So now you actually have a harder material with because of this working. And then if you repeat that process again and you go up now, you have to go up this curve. So you go up this from B to C, and then you go down and you can recover it. And this is your deformation. Okay, so you're permanently deforming this material. And this is just an example here of a blank of some metal that is sequentially stamped or cold worked, okay, into the desired final shape. And this is done for an awful lot of products. Sometimes if your stresses are too high, then what you have to do is reset the material, okay, and you can reset this material by annealing it and getting it back to its original composition, and then go back and continue your process. Okay, so this cold working is accomplished by extruding, bending, shearing, drawing, anything that's working the material. Okay, sometimes these are called wrought metals. Basically, when you manipulate or smash the metal, you're making a wrought metal, and you're working it below its recrystallization temperature, and you're effectively cold working it into its final shape. That makes the material harder. Okay, so this would be like your new stress strain diagram, something like this. Okay, due to strain hardening. Okay, if you do this only to the outer surface, say like in cold rolling, which they do in steel mills, then you can produce residual compressive stresses. Okay, sometimes they use cold working where you make a hole and you undersize it on purpose so that you can go in there and make it larger with a cold working tool to make that hole stronger. Okay, Sometimes this is also done for fillet screws and other places where you have stress risers. Okay, so cold working is done to increase the hardness of the material as well. All right. There's a lot of other methods. This is by no means exhausting. We have hot working, okay, where we have a material that's below its recrystallization temperature but at an elevated temperature, and you kind of get both the benefits of cold working and annealing. When you buy steel, you can actually get a cold rolled steel or a hot rolled steel. There's forging, that's your typical, banging of a material. Okay, so you can heat it up and then smash it into shape and heat it up again, repeat it. And obviously this is what blacksmiths have been doing for centuries. Okay, nearly all wrought material, rolled, extruded, ring rolled, forged, etc. Ductile materials can be forged. It creates stronger parts compared to a casting or machining, because if you can smash a material kind of into the final shape that you want it to be, then the grain structures of the material can be in line with the flow stresses of the part, and that could be a very good thing. It's a reason why a lot of your hand tools are forged and banged pretty much into their final shape, because it results in a stronger tool. And then you have extrusion. Basically, you heat up a piece of metal and smash it through a die, like a piece of pasta or macaroni, and then you cool it. This is actually quite economical. It's also used ubiquitously for tons of consumer goods, frames, windows, all sorts of stuff, where we can have these tiny little extrusions. We can do L brackets, channels, etc. for structural components, and it's a very good way of making materials. All right. So when we talk about steels, we can get all these different numbers. If you have a 1-0 steel, it's a plain carbon. It's basically steel and carbon. So if you have like a 1018, which is a pretty common low-cost steel, it's really just your plain carbon steel. If you get into these other alloys, you get into these different numbers and grades, then this is what they mean. So these are the alloys, and they are alloyed with manganese, nickel, chromium, molybdenum, nickel, etc., vanadium. So you can have these different types of steels, and they change the microstructure of the steels. They're made with very standard processes, and when you look at the number, if you kind of get a sense, you can maybe remember what's in there from their different series, okay, the different series numbers. But this is sort of the mapping. Here is sort of the strength versus ductility. So really what we're doing is, when we're talking about all these different materials and steels, we're talking about sort of what kind of properties do we need? Do we need something that's really strong and somewhat brittle? Do we need something that's very ductile and can take a lot of energy? Do we need something that's kind of in between? So you really can operate all over this map in the stress strain diagram, and obviously costs and availability and all those things will come into play. But these are the things, this is the space that you have to operate in as a designer. So these are just some of the material properties. These are taken straight from the book. Okay, so what's interesting here, these are your stiffnesses. So you can kind of look, if you need something that's really stiff, then you can take a look at this stiffness. Obviously steel is extremely stiff. Aluminum is much less stiff. Okay. And you would need like more aluminum, to a larger cross section of aluminum, for example, to get the same stiffness as you would for steel. So, although aluminum is lighter than steel is significantly stiffer. So you have these trade-offs. But interestingly enough, this is your tensile strengths for aluminum and steel here. There are some aluminums that actually exceed the tensile strengths of some steels. So these higher grade like alloys like the 7075, aerospace aluminum, is all the way above 75 in its tensile strength. So if we come up here, we're on the order of like, your 1030, 1040 steels. So a brief note here is that, every material property that you read has some statistics associated with it, right? Obviously, if you're doing a stress strain test for some material, you don't expect to get the exact same value down to 10 significant digits every single time. So it's good to remember that the values that you get, they have some variation in them, and you can't necessarily assume that like the published value is going to be exactly the value that you're going to get for that material. So you should understand that there's some statistical variation when you look at the properties of materials. You ought to be able to get that information for some materials. Sometimes for some structural elements, they might report like the minimum values. But in general, it's good to keep in mind that, materials have some, statistical, probability distribution around their mean. Now, this is a Gaussian distribution, which we think as a uniform normal distribution about the mean. So if we were to test, the strength of steel for, 1,000 samples, we might expect that strength to look something like this. And we can kind of get a feel for how tight those values are to their mean based upon their standard deviation. So if we have the measured data, we have the mean of the data, then we can calculate the standard deviation. And then we can kind of get a sense for what this probability distribution looks like in terms of the standard deviation, that actual sample, and our mean of the sample and over the standard deviation squared in that interval. So if you don't have this data, then you can still kind of maybe assume like a standard deviation from the mean. In this case, for steels, the strength of steels is usually within 8%. What that means is a standard deviation of 8% within the published data. So if we use that 0.8% for the standard deviation, then we can get a reliability factor that's based upon these standard deviation distances from the mean. Okay, so if we want a reliability of 50%, then we can just take that value to the bank. Okay, if we want a reliability of 90%, we can take the published value for that strength and multiply it by 0.897. Now, if we want a 99% confidence that that value is going to be within that threshold, then we need to take the published value and I'll only take about 80% of it, multiply it by 0.814. Okay, so as a designer, you kind of just need to make sure that when you're pulling data, that you understand that this data, has some variance to it, and if it's critical in your design, you just need to make sure that you are designing, away from that. If you need that value to be very highly accurate, then like say if you're going to get the yield strength of that, say some steel in your design, and you have to have a 99%, accuracy, well then really you need to reduce that published value, okay, and multiply it by a different number. So this is actually should be 81814. All right. So hopefully that makes sense. So statistics is something that we have to keep in context. Now, in your book, also discusses polymers, composites, ceramics. So much of machine design is focused around metals, which is where we focused our attention here. But I encourage you to read chapter 2, okay, and make sure you kind of get a high-level view of these material properties because they will be useful for you as a designer. Now, I only have 2 more slides. This is the first one, and just kind of want to make you aware of tools that are available to you. Okay, so Ashby has spent a significant portion of his career producing graphs like this, and he summarized them in his book, which is Material Selection and Mechanical Design. It's a fantastic book, and it pretty much takes all of the properties for all of the materials and plots them on different plots. Now, this plot in particular is your Young's modulus, which I think of in terms of as stiffness. So this is your stiffness versus density. Okay, so if we have to have a very stiff, lightweight application, and we kind of know the stiffness to density ratio, then we can create some constant, and then whatever that is, we can map it out through this graph, and then we can see all of the materials that will satisfy that stiffness to density requirement. Okay, so in here, if we go up from here, let's just say that this is our stiffness to density requirement is C, some number. All right, and we go from the left all the way and we follow this line. Well, the materials that satisfy the stiffness to density are woods, okay, pine, oak, ash, balsa wood. Then we get up here, we get into laminates, you know, carbon reinforced laminates, glass reinforced laminates. And then we get into some other materials. Okay, we got magnesium alloys. We smash right through those. Okay, porous ceramics. Okay, and then over here we have all these engineering alloys. Okay, so this is like sort of the space, this big circle here of engineering alloys. And then we go through, these are titanium alloys, zinc alloys, copper alloys, nickel alloys. Looks like steels, magnesium, tungsten alloys. Okay, so we can get this sort of this mapping of what is possible. Now, obviously, we'd have to go back to some of his other charts, which deal with cost or maybe availability or other properties we care about. But this is a way of us exploring space that's not necessarily super visible to us if we have specific requirements for design. In this case, we needed a stiff, lightweight design. We come up with some metric for that, and we can take a look at where the materials line up in this chart. It's a good book. Highly recommend you get it. This is another chart. In this case, it's strength versus density. So now we need a strong, lightweight material. Okay, in the same way, we can create some requirement of strength over density. And again, we're passing through woods, but in this case, we have a slightly different shape of this graph. And that kind of shows these different materials. Okay, so these graphs can help the designer select materials that they may not have thought of before and make you aware of different space. So the point here is just to really make you aware that these tools exist to help you go through the design space, and can help you identify materials to solve more challenging problems than just going and picking your 6061 or your 1018 or 4140 steels. Okay, so in summary, when you design something, we're always designing for performance, but we're also designing against failure. The materials that we select are a big deal. Obviously, we're not going into great detail about all this stuff, but I hope this is a good sort of like high-level view of the things that we kind of need to keep in mind and trade-offs in some of the material properties such as strength and ductility. So there's a lot of references to kind of help you go from here, but hopefully this is a good reminder of sort of like the materials and the material space and some of the material processing options that you have. So we'll stop here. Thanks for your attention, and I will talk to you soon.